Welcome to a Cisco meeting. You are entering the meeting now.
Okay. Hey, morning, everybody. Morning. Oh. All right, maybe I should say afternoon. This is not exactly morning anymore. Still stuck in the morning mode. Okay. So good news for all the class. I just finished grading the test, and I taught 3 years of this class straight. And this class did the best among the 3 years on average. So I'm very proud of you guys. This is very good. So keep the momentum going, okay? And same for the ERDIC side. Most of you did very good. Good job. So I'm not going to hand back the test, but if you guys want to know exactly, please just send me an email. I'll have the office hour tomorrow afternoon from 4:30 to 6 p.m. for you guys, okay? You guys feel free to stop by. I'll explain every problem if you have trouble, okay? So now we've closed one chapter. That's about chain statistics and chain conformation. So for this class, we're going to move on, and we're going to talk something not totally different, but abstractly they're quite different for the chain conformation. So if you guys has had a little bit of head start about textbook, you will see we're going to start talking about chapter 7 about polymer solutions. This particular chapter is all about how does a polymer behave in the solution state. And especially we are interested to the question, how does polymer mix with each other, okay? Mixing is a very important topic, and throughout the course I will talk about the mixing behavior of polymers. So when I talk about mixing, what comes into your minds in terms of mixing? Anything? Please, Sonia?
Homogeneous versus heterogeneous.
Homogeneous versus heterogeneous. Homogeneous, I assume it just means they mix well. Heterogeneous, I mean, they're not mixing, right? So you get phase separation. So we will talk about something about in this chapter. So we will talk about mix. So how do you actually know if your material would mix or not? I heard Gibbs free energy. Okay, good call. And what we will use particular Gibbs energy for this particular chapter is talk about how Gibbs energy can help us understand how those two components would mix each other, okay? So we can start with talk about lattice theory. So that would be chapter 6.2, which is generally lattice theory. Okay, so this lattice theory will tell us about if your material would mix or not, if they're small moleculars. We're going to start with easy. And you can think about this chapter this section, 7.2, which strictly talks about you have a mixture of small moleculars A versus B and how they mix. So realistically, you can think about mixing toluene or hexane or any two solvents when there is no connectivity with different parts. Okay, once we finish this part, probably it takes 2 lectures to finish this because we're going to talk about enthalpy and entropy in terms of mixing and how they come into play. After we finish this, we're going to start to talk about a very famous theory called Hagins Theory. Flory is one of the Nobel chemistry winner in 1974, so he's very well known for his contributions in polymer science. Hagins theory will tell you, this will tell you mixture of polymers. Okay, so if you read the textbook, it will tell you what's going on in mixture of polymers. Well, 7.2 will tell you what's about mixture of solvents. Okay? So going along these thoughts, we now going to finish those 2 chapters and understand what's generally going to happen in terms of mixture behavior, polymer, solvents, or any 2 of them you can pick. So what else? Any thoughts in terms of developing theory for polymer in solution? Entanglement is important, but I would defer that to our new faculty, Drew, talk to you guys about rheology. So he will talk to you all about entanglement in terms of polymer. This mostly in mel. In solution phase, Dr. Simon will teach you guys about all the dynamics of the polymer chain, all the different Rouse model, etc. So in the Flory-Hagins theory, there's a very critical parameter called Flory-Hagins parameter, which is usually written as a chi. So this is the most characteristic polymer physics parameter because none of the other field use that much. Polymer scientists like to talk about chi all the time because this is a single parameter. If you speak about chi, you can get a pretty good understanding if your material are likely to mix or not likely to mix, or what is the interaction between 2 components. Okay. So in the textbook, we would take a small detour in terms of talk about phase behavior. We would take a detour to talk about osmotic pressure. That's usually chapter 7.4. And this particular chapter deals with how do we understand polymers behavior in solution and how does it would affect Flory-Hagins parameter, okay? And we will learn chi parameter would relate one particular parameter in solution, probably called the secondary viral coefficient. We were not going to talk too much about that, but they are related. So from the chi, we can understand V2. So those 2 parameters talks about the same physical phenomenon, how your polymer and solvent will interact with each other. So these 2 parameters are interconnected. That's why we're going to take one short step to talk about osmotic pressure before we actually return to probably the most important chapter for this section, for this whole chapter, called phase diagram. This we will talk about at least 2 classes for the phase diagram. And this would be the ultimate, I would call it a map or a guidance for you to see how does your material would mix. Okay, in the phase diagram, you usually plot as if you would form one phase, homogeneous phase, or you're going to have phase separation. And this phase diagram is typically also plotted as different volume fraction. Sometimes if you had a little bit A into B versus 50-50, they would, show different phase behavior. And from the phase diagram, you would be able to read it. If my polystyrene or polyethylene would mix, and how much they would mix, and at what temperature they would mix. Okay? So this would be the phase diagram. And at last, we're going to revisit a topic called polymer chain in solution. And this comes back to chapter 7.6, which going to talk about in the good solvents and how those good solvents can be linked together with the parameter of the chi and the second viral coefficient. It's quite a journey, huh? So we got 1 month to talk through all these points. And so the plan is similarly, we roughly going to have about 8 lectures. So I'll try to stay roughly plus minus 1.2% of the lecture chapter. So each class I will talk a little bit about focusing on one section, okay, and walking along these lines. If some of the longer sections, then I'll break to 1.5 or 2 lectures. So please stay on the top and take a reading of the class textbook again, and those are pretty well written. Okay, so let's get started for today's lecture. So I'll give you an overview of this whole month. So let's focus on the detail. 7.1. So we're now going to talk about mixture of polymers. And somebody helped me start it today. We're going to talk about thermodynamics of all the polymers, okay? And to understand this, we want to have a quick review of what is thermodynamics and how does these help us to understand today's lecture. This is somehow a little bit distorted, so we don't have much room to play with. So let's see if we can rotate make it work. Oh, it's the same. Forget about that. So what we're going to start is talk about polymer thermodynamics. So we want to start talk about what is specifically thermodynamics we want to talk about. So first we want to talk about solution. So if we talk about polymer in a solution, what happens is it's usually homogeneous. You have a polymer chain dissolving in a good solvent. You typically have a thermodynamically stable solution. So what specifically this means is you're going to have a polymer chain swimming around in a good solvent. It's thermodynamics if stable. Specifically, that means if you leave it for a long time, you wouldn't have changes in terms of property. Assuming your solvent is very nicely sealed, you don't have anything escape out the system. By the way, the notes are already up in the Canvas, so you guys should be able to download it for the new one. And for the polymer solution, it's quite a unique system because there's a large difference in the size of these polymers and solvents. And we will come back to this size effect again. One of the key differences between mixture of polymer blends versus the solvents blends is the size of connectivity. And anyone could guess what the connectivity would influence in terms of mixture process. Here we're specifically talking about entropy and enthalpy process. Anyone? Please, Sonia?
Maybe the more connected the polymer chain is, the less able it is to mix freely in the solution.
That's a good point. You point to the right answer. What causes the difference of mixture? what it causes the driving force for them to mix or not mix. That's the whole topic of today, and we're going to talk about Hagins Theory, or a little bit before that is the free energy we're going to talk about. So it's very important actually to understand these phase behavior. So how can you make sure your polymer would mix, not only at the small scale, but also at the large scale?
Are you talking about polymers, like two polymers both dissolved in solution? So two separate
No,
types of chains?
you can talk about that. In specifically in this lecture, the scope is basically binary. Either going to be solvent versus solvent. So you can think about it's the case of toluene mixed with hexane. You just pour two solvents 1:1 ratio, mole ratio. Then they would stir them up and see if they mix. And when you think about the second case would be you have a polymer versus solvent. So you have a polymer chain, 1 mole of polymer polystyrene, and you put in maybe 10 moles of toluene to dissolve it. And you still have the binary case, okay? And more complicated would be you have polystyrene and PMMA. However, you just heat them up above melting point. So they behave like liquids, but they still are somehow connected, right? So a good starting point is...
I would think
So,
it was,
hmm? Yeah.
You said that if the connection is at nanoscale, I would think the entropy would be higher.
Well, actually, the other way around, and that's what we're going to chat about, what's the entropy of mixing. So let's continue a bit. This mixture behavior is very critical when you consider you want to design a new product or when you want to develop something new. Think about the cost of making a totally new polymer, start from scratch, versus simply you have a stock of different material you can mix and blend them to change their macroscopic behavior. As long as they don't phase separate hugely, they would tend to behave like one type of material and have a unifying property throughout the material, okay? So if I'm a CEO or CTO of a company, I certainly don't want to overspend the money while developing a new water bottle, for example. I just want to try. I can source those home polymers and try to mix them with some surfactant or compatibilizer to make them blend, okay? We talked about motivation, so everybody agree this is important. So now let's review some of the fundamentals of thermodynamics. So when the substance mix, there's changes in the Gibbs free energy, and everybody heard about this, delta G. So all of them have taken thermodynamics class. Not everybody. Who have not taken this class? We have about 5. Okay, all right. We can review a little bit of the whole process. So this is rather comes into very abstract term in terms of what thermodynamics. But in a key sense, we can generalize the process by considering the changes in the process before and after in delta H. This is called enthalpy. Or basically, it's actually pointing to a little bit wrong direction. Seems like the slides shifted as well. So enthalpy is delta H. Okay? Delta H means the changes in terms of heat throughout the process. If you have delta H is negative throughout the process, means your process is going to give out heat during this from the beginning to the end state. If the delta H is positive, that means your system will take in the energy while there. I'll give you an example. If you think about water and sulfuric acid concentrated, and this is what, like the safety, the perfect example of the safety class. They teach you, don't mix in. If you want to mix in, follow the rule of pulling. I'm not a chemist, so I'm trying to get this right. You want to pull the sulfuric acid through the side of the beaker, so that very little by little. And after the mixture, you will feel that the whole mixture or diluted sulfuric acid is very warm or can be even hot. So this process is an example of your mixture process gives out heat during the mixing. There's also a process that takes the heat. Okay? So enthalpy is talk specifically about heat changes during the process. So delta H can be positive or can be negative, or even be zero, means there's no heat difference before or after you change. How about this? S. Entropy. Somebody help me with how can we understand the entropy for the system? Masonia?
The more entropy, the more chaos, and the more likely things are to be able to react with one another?
Right. Entropy is a describer for the ordering of the system. Specifically, order, we can think about a nice, clean daycare room. Teachers put away back all the toys into the drawer. Floor is clean. Entropy is low because everything is placed in order. When in the evening you pick up your kids, the whole room is like after war zone. You got teddy bears and maybe hanging on the roof or anything like that. The disorder state is much higher, right? All the molecules are more randomized. And this is called high entropy state. And in this state, your delta is higher. And even more interestingly, the thermodynamics tells us the system always spontaneously want to go to high entropy state. What that mean? That means everything tends to go disorder. If you own a house, the other problem you would have is weed growth in your yard. You just can't stop the nature to disorder your yard. It just everything grows. All you think about in the case of what we care is polymer, the order state is crystalline structure. What disorder state is more associated with amorphous phase. While when you heat the system up, you can drive it into more disorder state when all the polymer chains start getting rendered. Okay? So the Gibbs energy is given by a combination of enthalpy change and entropy change in the system. And we know when delta G is, this means the process would spontaneously proceed. Okay? That means if your system like to give out a lot of heat, there's a lot of driving force for the system to go from the process starting point A to the end point B. Okay? Very simple, very easy to understand the process. So, any question for this part so far? Now the question for us is how can we describe entropy and enthalpy for the molecular system in terms of when we mix two components into one, okay? Well, this is a bit complicated. What solution thermodynamics basically tell you, we need to describe the delta G into the mixture of solution versus pure compounds. So let me give you an example. Consider a box of solvent molecular A. You have all kind of solvent molecular swing in the box. One beaker, solvent A, Second beaker, solvent B. When we pour it into the same large beaker, you would have a large box and you have chains swimming around. So in the mixture process, you have changes in both delta S and delta H. So what we need to consider is actually free energy state let's call it GA. This would be the free energy for solvent B, and you have GAB, right? So the changes of system's free energy, delta G would be the final state minus where we start off. All basically changes in the system. Or more specifically, if we apply all the G as enthalpy and entropy, we need to consider both. What would be the entropy difference and what would be enthalpy difference before and after into the mixing. Quite straightforward, huh? Any question for so far? No question? It's relatively abstract, right? The other thing we need to understand is there's one more term called chemical potential for a system. Can anyone guess what the chemical potential would mean to you?
It's the potential for chemistry to occur in the reaction.
For a specific component, right? So the chemical potential would be the potential for a given compound at a given state, okay? So if you want to write the delta G, that would be considered to be a partial derivative of individual component. We can understand if we take a partial derivative of this to T, we can get S. In other words, if you have partial derivative of free energy, so temperature, you can have S. Because H doesn't have a temperature component, if you take a derivative, that would be the case. Okay? So everybody is comfortable with this part? So let's get on to talk about what is partial molar quantity. Partial molar quantity is a specific state talks about at the 1 molar level, what does your material behavior look like? So here we give an example about what is a partial molar volume for the polystyrene in solution. Okay? So if you look at what we are trying to address here is we have 0.482 grams of polystyrene with a molecular weight about 220 kilograms per mole added to 117 milliliter of toluene. We now have increased slightly in terms of volume. If you look at now, the final solution volume is up to about 117.22 cubic centimeter. We want to understand what is the partial molar volume for the polymer in solution. Read what the question asks. What is partial molar volume for polymer in solution? So this particular question wants to understand what it actually has in terms of if you divide the volume of the whole system, take a derivative to the moles of your polymer, you would have what is called partial molar volume. Or the other way you can think about the question is, how does 1 mole of polymer has a certain volume in solution state? Okay? So if you combine in this, the volume of polystyrene, or partial volume, basically you can understand as the volume difference before and after mixing. We have after mixing is about 117.22 minus 117.11. You would have the delta V. That's the changes in terms of volume. We can also get what's the molar, how many moles of your polystyrene we added in, because we tell you how much we had polystyrene. You have the weight, you divide by molar mass, you get how many moles of it. We have divided the mass, you have about 2.19 power of 10 to the minus 7 mole. And now you can calculate how much partial molar volume of the chain, okay? Because you have volume change, you have how many number of mole. This will tell you how much volume per mole of polystyrene occupies in the solution state, called partial volume. And the point of doing this is now if you consider for individual chain block, your volume of polystyrene in each repeating unit is slightly smaller. We can get what is called a number of chains in repeating block. That's a repeating unit for polystyrene in terms of molecular weight. That's total molecular weight. We can get number of repeating units for this molecular weight. Combining two, you can also get the molar volume, because we know the density of our material. If you use this to divide by density, you will get the same. However, these two values doesn't match if you compare. The molar volume for this is 10 to the power 5 in the bottom. If you still need to divide by molecular weight, but if you do that, they still will be vary quite a lot. So partial volume in this case tell you how much the polymer occupies in the solution states versus how much in how can we call it, in an ideal the chain case versus in solution. Any question for this part? Sonia, please.
So I understand how to calculate it. When you see that the partial molar volume of the polymer is larger than the corresponding of the pure material, does that mean then that it is going to mix well?
No, it's not related to any mixing. The mixing behavior will be deferred to when we talk about Flory-Hagins parameter. And we're just going to talk about, we actually will have some time to discuss about that. So let's talk about the slides on this particular one. When you consider you have two materials you want to mix, we now need to consider what is the delta G changes in the material. So specifically when you mix two material, we want to consider what is before mix states and after mix states, right? So let's break it down. In this class, we're going to talk about one specific question is, how does your material behave in entropy before and after mixing, okay? So the next topic is we're going to talk about entropy of mixing. Again, to help you guys understand, I will give some more detailed example of what we're going to talk about. Why don't we start talk about examples of mixing 100 molecules, 100 molecules of polystyrene. No, let's do small molecule first. Let's do toluene. If we mix these two, how do we understand their mixture behavior? So let's use this example again. we have solvent A, solvent B, and mixed into solvent AB. And to tackle this problem, we need to break it down into two parts. First is your molecular has different interactions with each other. Think about the interaction parameter between toluene and toluene versus hexane versus hexane. After you mix in, now you not only have the molecular force going to be interacting with each other, but also with the new molecular. And how can we separate the interaction? So that's related to the enthalpy. Enthalpy discusses about the intermolecular interaction. Okay. So second is entropy. When you consider, well, we mixing the solvents in here in A and B, how can we consider the entropy? Will it go up or go down? It will go up. Why?
It's becoming more disordered.
It could become more disorder, right? So, or you can think about the other way. You have a pure solvent A, a pure solvent B before mixing, and after mixing, you have sort of blends of A and B. And the disorder goes up because certainly it costs quite some energy to separate them to get a pure product on an industrial scale. Okay, right? If you want to separate different mixtures, it certainly costs the energy to distill them or the other ways to purify them. The question is how much entropy increase we can calculate. Any idea how we can get the entropy for the system before and after? How do you calculate the entropy for the system? I think this might be beyond everybody's knowledge. If I haven't learned before, I wouldn't be able to get that. What would be it?
Isn't there a maximum relation that gives it? You can measure like a change in volume after change in temperature.
Not that. So there's it is defined by a Boltzmann equation. Boltzmann is very quite simple in terms of definition. So entropy S equals to number of possible state correspond to. So this is defined as number of possible state for the system. What does this mean is if I have this classroom has 20 chair, we have 20 of you, how many possible states we can occupy different with each other. If you guys sitting in a different chair, it's called one different state. So think about that. If we only have two chairs, two students, there's only A sits here or A sits on the other side, then there's less entropy. Well, when the system is getting bigger and more complicated, your entropy actually goes up quite. Your entropy goes up quite dramatically. Okay, please, Anya, question.
Is that where factorial would come in with the higher entropy system?
We're just gonna get into that in a
Sorry.
second. We just finished. We're just gonna talk about just in 1 second. Okay, and K is called Boltzmann Constant. It's a classical parameter related to quantum mechanics. So K would be equals to Joule multiplied by pi minus 1. Okay? 1.38, 10 to the minus 23. It's a constant and doesn't change it versus different system or different material. So now you can see, if we know this equation, we can sort of start to have some knowledge or possibility to calculate what is entropy of your system. Let's start with some simple one. What would be the entropy for a pure solvent sitting by itself? 0. And how do we get 0? All possible states are identical, right? So if we consider we have 100 of these different solvents molecules sitting around, and if we now say we now divide each box by a lattice, because the lattice theory is very easy to understand. Now we can fill the lattice with different molecules. If we have a grid of, let's say, 6 by 6 box, we have 36 molecules. No matter how we fill it, it's always going to be a box with filled molecules. You can think about, you go to the candy shop, everybody likes eat sweet things. No? Some of you guys? Yeah. Let's shop at C's Candies. When you buy it, they have a box. Although in that case, each candy is different. But think about if you pick the same variety of candy in a 5 by 5 grid, you're going to fill each grid with candy. And no matter if you throw them out and you start fill back in for these candies, they will look like exactly the same because all the individual candies are identical. There's no difference. So like Surabi said, all the possible states are identical. So if you think about this, possible state will be 1, because everything is the same. Log in 1, multiply constant, this will be always, entropy of the starting point is always going to be 0, okay? If we have to write 1, we can write SA would be equals to 0, SB equals to 0. Now, this is a little bit tricky. How do we consider the entropy after we mix them? How do you guys consider that? Okay, let's do a simple experiment. If you have consider a box about 4 by 4, you have 4 grids. In terms of having this much molecular, we consider 16 molecular A, okay, plus, let me change a different color and get a second set of box. You have 16B. Now when you mix them, your total option is now become a large box. You have sounds like a supersized C's candy, where now you have a chocolate flavor and banana flavor. So how can you fill the box, and how many different possible ways you can fill it is a question we're going to ask today. 1, 2, 3, 4. 1, 2. We have a grid of now 4 by 8. And we have total of 32 molecular. And 16 of them are white banana. Maybe I should call the B is strawberry flavor. It matches my chalk color. How can we do that? And we actually had a similar problem we discussed in the random walk. And I'll give you guys a hint. What's possible ways we can address that? Think about the random walk. We have similar problem. If we needed it ended up in an arbitrary number, we can take some positive step, some negative step. So it's became a statistical problem, right? Any thoughts? Any brave idea how many possible we can fill it? So we can think about how many total possibility we can fill the candy box. We have 32 of them. You know, the first one, when we fill it in, now the box is full, right? Now the grid is occupied, so we can pick any one, let's say here. And for the next one, candy you want to add in, this one is taken, so we can only pick the other one. Let me take turns to fill it. The other candy gonna be here. So we can repeat the process. So the total weight of when we fill the box is equal to 32 factorial, right? Total number. But as I fill differently, this will be full eventually, but there's going to be some overlap between cases A and cases B because all the reds are identical. So effectively, we just need to take a factorial of number of red and number of white color. So that will be our total number of possible states we can fill for this particular box. If you guys remember the random walk, we did a similar calculation where total possible ways you can reach to the end state of x will be equals to total of number step, total of positive step, and total of positive step and total of negative step, right? Multiply. So those two are the exact same problem. Everybody remember this process? So generically, we can write, if we have n number of molecular A and n number of molecular B, what would be the total possible of states? Come on. We can do this one. I tell you the number of molecules. Instead of 16, we now have a generic MA.
M plus, or MA plus MB factorial over M factorial B factorial.
Right. Right? That would be the possible state. So we are very close. Ladies and gentlemen, watch. We just need to calculate a line of number of possible states. We can calculate what is the entropy after we mix the two. We know before mixing, it's going to be 0. All the possible states are exactly the same, but we just need to know what is this parameter is. So if somebody can help me calculate this. I want the entropy. We can start with more. We can start just to use a generic term to calculate what the entropy of mixing. Okay? Then we will go back to get the enthalpy. what would be the entropy of mixing? We heard about that. Your possible state would be N1 plus N2 so we can do several things to make the process easier. First, we need to learn a mathematically simplified terms, because when we K is a constant, so this would be equals to K ln N1 plus N2 factorial right? I think you guys a little bit harder to see, so let me repeat it here. So we basically says S would be equals to ln okay. Everybody gets it? Let me make sure I can show you guys just one slide. Okay. It's a bit smaller. Everybody following? What we are trying to do here is to calculate what the entropy for the mixed state. So to solve this particular equation, K equals to ln M1 plus N2 divided by N1 and N2. How can we address this one? It requires a little bit of math, but not too hard. Let's get into that. I'll write here so everybody can see. So we will have a K multiplied by, what is ln in this term? It can be simplified as ln N1 plus N2 factorial minus ln N1 minus right? This everybody gets it? This would be just expansion of what is individual components. Now the question is how can we get ln just general m factorial? There's a shortcut we can learn mathematically. This called Polystyrene expansion. This would be equals ln m. I think it's minus m. Let me make sure. Yes. Okay. Everybody gets this? Okay, now we can just add everything into the term and calculate what is exactly the final value. So if we insert this in here, this expansion for this part for this first part is ln factorial m1 plus n2 is equal to this, and for the second part minus, if you do this again, you're going to have n1 ln n1 plus N1, right? And you have the similarly has N2 term. So this coming from this term, this particular one. So we did nothing crazy except expanded each line n factorial. All right, almost there, one step. So these two terms will cancel out with this m1, n2 will cancel each out. And what we left is basically 4 terms. Very easy. If we write k that's how you could simplify this. So we can separate out, take n1 line, m1 plus n2, just to regroup all the n1s into one box. So, Lena, please.
I'm a little bit confused. It's because in the first term that you expanded, you did minus m1 plus m2.
Mm-hmm.
And the second and third terms that you expanded, it's plus m1 and plus m2.
Yeah, so the difference is because here we have a minus term just before that.
Distributed it.
So I already distributing it. Okay.
Thank you.
So we finally simplified the entropy difference. Entropy, not difference. Entropy of the n states into a very simple relationship. And we can even make it further, one step further. Because n1, n2 is just number of molecules. We can take one more step. How about we define this term? If we know what is volume fraction for your molecules in the mixed states, if you consider just a generally m1 plus m2. So volume fraction, let's define volume fraction. How many Sonias is in this class? There's only one, but there's 16 of the students, so we can define the n1 will be equals to m1 plus n2. So the volume fraction, let's call it actually x1. Volume fraction so your volume fraction is critical. Your volume fraction would be equals to number of molecular in the mixture state divided by total number of it. So what is this equals to? Inverse x1. So it will be equals to n1 line x1. Okay? Plus n2 line x2. Line minus 1, you can pull this term out. It's basically negative, right? So we can simplify this as that's the entropy for the final state. You got a Boltzmann constant multiplied by what is m1, what is x1, what is n2, and x2. So now, what would be the entropy of mixing, let's say, 100 molecular toluene and 100 molecular hexane? we have a general recipe. So someone help me. How do we calculate the entropy of mixing 100 molecular of toluene and 100 molecular of hexane? Please. Sam, how about you?
I would say it's equal to negative 1.38 times 10 to the negative.
Slow down, slow down. I'm older man, so I can't follow. What is that?
It's going to be final state minus the initial state. The
Yeah.
initial state 0, so it would be negative K. Times M1, so it would be 100. Times ln of, looking at 100, so 1/2.
Okay.
100 ln 1/2.
Someone can run a calculator for me? What is logging 0.5 would be? How about Surabi? Can you help me? Thank you. What it would be? Minus 0.69, right? That's just to multiply by 2 because they are identical. We keep the k term. So it's going to be 138 k. That's entropy of the final state. K we already talked about. So one of the key message of today's lecture is when you mix two materials, the entropy would go up. The initial state of 100 toluene is 0. The initial state of hexane is 0. After we throw 100 moleculars into a beaker, shake it, now we have an increased internal entropy, and we just calculated it. It's going to be equals to this. And again, K is just a Boltzmann constant. We already speak about that. And it's going to be around 138 K. So you have a negative increase in entropy. We haven't talked about enthalpy. For today's discussion, let's assume enthalpy is not our business. Then you see, entropy will go up. They will mix, right? How about we have throw just one moleculars hexane to toluene. All right. Everybody got this one? I'm going to erase this. How about we have a second classmate help us what this would be? Entropy, 1 hexane in 100 toluene. I need another volunteer. We need a different one. How about, okay, Waylon, please. Yeah, let's try it. Let's try it. So how do we calculate that? We talk about everything there. We have a perfect formulation we can follow in terms of calculating the entropy, right? Right here. And 1 would be 100. Would be what this would be. If it's 1, log 1 is 0, so we cannot be putting it down as 1, okay? And right? I'm genetist. Perfect landing. Okay, somebody help me. What is this? I'm not going to do it. So Can someone help me? Someone with a calculator?
In my brain.
So the other one, 50, no, 100 by 100, we calculated, it's about 138, okay? How about this case? What would it be? Huh? 5.6K. We already have it. Okay, good job. Thanks, Levi and Wayland. So you can see one of the key lessons in terms of lattice theory, or what we have discussed today, is entropy, no matter how you consider in terms of mixing small molecular, it's always going to go up, because after mix, you always have going to create some sort of disorder introducing two-phase. So entropy always favors your material to be more mixed. Let me say one fun thing and kind of very painful to me. I recently bought Legos for my kids. He used to play these Duplos. Those are giant Legos, which are much easier to clean up. Now we just got I think it's a 1,500 piece of Lego. Now these are just classic, so they come in and very nicely, each one packaged by a different color. So a red, blue, and each one has about 100 pieces. I put Ziploc, I open it, I put it, I sealed it, and say, Max, whenever you play, you have to take one color and you cannot mix them. He obeyed the rule for 2 days, then one day I come home like perfectly mixed. Entropy goes up dramatically. See? Same case here. So question?
I was just curious. When we have them completely unmixed,
Mm-hmm.
we're just calling entropy 0, right?
Yeah.
Okay.
For this particular just isolated case, you only have material by itself. Entropy should be 0. So effectively for the system, we need to calculate it not S in the final state, but to be more accurate, we need to consider the mixing process should be considered delta S. So this would be the final minus S beginning. This happened to be equal to 0. That's why we say entropy differences happen to be related to the final state. So one key take-home message is if you mix two things, your x1 or x2 will be always below 0 and 1. When you mix two things, your volume fraction cannot be smaller than 0 or larger than 1. And log n, so log n x will be always be a negative value, because log n 1 is equal to 0, so anything smaller than log n 1 will be always be negative. Just mass, okay? If you consider this equation, so no matter how we mix different kind of numbers, either 1 to 100 or 100 to 1, or 50-50 or 20-80, the entropy always going to go up. So that favors your material to be mixed. I think that's what I want to talk about today. So next class we're going to talk about enthalpy. So how does the enthalpy difference would happen in terms of mixing? When you mix two materials, how does the enthalpy change? Anyone want to contribute some knowledge? Will it be always plus or always negative? So we have a vote. How many think that will be depend? Okay. How many think so will be always plus? No? Always negative? Neither? All right. It's very hard to get you guys into a trap. It will depends. And that's actually related to the Hagins theory we talked about. The chi parameter is one of the only parameter going to describe if this will be enthalpically favor or enthalpic penalty, okay? And we will spend next class to talk about that. Okay? Any more questions from you guys for entropic contribution in terms of mixing? Okay, if no more, we can finish the class early.